Good morning, gentlemen. So today we are going to continue on with our discussion of modern physics with what is today known as Einstein's theory of special relativity. He actually had two theories of relativity. One was special relativity and one was general relativity. We're going to talk uh, today mostly about special relativity. Now, this is one of those things where everybody kind of thinks they know the theory, all right? And the theory of relativity, according to most people, is the equation E equals mc squared. Now, that does play a role when we get to momentum, but that will be the next video that you see. But in reality, the E equals mc squared formula has little to do with Einstein's theory of relativity. So at this point, let's just jump right in, shall we? So before we begin this, we need to talk about what's called an inertial reference frame, okay? And by definition, it is a frame of reference in which all of Newton's laws are valid. So all of the classical physics stuff that we've been talking about since September are valid laws, right? Einstein realized that in certain conditions, these laws are violated. And so Newton was wrong, not because he was wrong in terms of what he knew, but in the idea of space and time, Newton and his ideas no longer become valid. Now, the reason for this is that we think of the Earth as an inertial reference frame. We think of Earth as essentially non-moving. But in reality, and this is what Einstein realized, it's not an inertial reference frame. The Earth is hurtling through space at astronomical speeds, literally astronomical speeds. And so we need to think about that in terms of relativity. Now, in terms of the actual idea of special relativity, there are two major assumptions which Einstein referred to as postulates. And the first postulate states that the laws of physics are the same in every inertial reference frame. Seems reasonable enough. All of Newton's laws, F equals ma, and the laws of motion, all of the kinematics equations that we talked about in September, all of those things they hold fast, they hold true in an inertial reference frame. And so, for example, if you're standing on the ground, all right, and you've got a buddy standing in the back of a pickup truck, and he throws you a baseball at a speed of 60 kilometers per hour. That's a reasonable speed for a thrown baseball. All right. So the two of you are just having a catch. All right. There are three possibilities. All right. We're going to assume that you are stationary, but the truck can be doing one of three different things. All right. For example, if the truck is completely stationary as well, then both you and your friend in the truck are in the same inertial reference frame. And so when he throws the ball at you at 60 kilometers per hour, it's going to reach you at 60 kilometers per hour. No real question there, I wouldn't think, right? It would just be like him standing on the ground, right? The truck's not moving, so he's stationary, you're stationary. The ball travels between the two of you at the speed of 60 kilometers per hour. But what if the driver of the truck threw it in reverse and was moving toward you at a speed of 40 kilometers per hour? Well, then, if your buddy throws the ball at 60 kilometers per hour, the ball is actually going to reach you traveling at a speed of 100 kilometers per hour, right? The 40 kilometers per hour for the motion of the truck, the 60 kilometers per hour for the motion of the ball, it will reach you traveling at a grand total of 100 kilometers per hour. Now, there's a third scenario here, and that is if the truck is moving away from you. Right, so the guy puts the truck in gear, in drive, and takes off at 40 kilometers per hour. Your buddy throws the ball at you from the back of the truck at 60 kilometers per hour. Well, now the truck and the ball are moving in opposite directions. And so if you subtract their relative velocities, the ball only reaches you at a speed of 20 kilometers per hour. All right. And so those are the three different uh, frames of or possibilities for a frame of reference in that case. Now, the second postulate is really the one that leads to the idea of special relativity. All right, the first one is really more of an overall kind of thing, but this one says that the speed of light in a vacuum, measured in any inertial reference frame, has the same value, no matter how fast the source of light and the observer are moving relative to one another. All right, no matter how fast. Now, this postulate seems to be a little weird, all right, because what we're essentially saying is that the speed of light is constant no matter what speed the source of the light is traveling. But because light is an electromagnetic wave, it does not require a medium to travel through. And so its maximum velocity is constant. And this is what Einstein in 1905 wrote his first major paper about. And essentially, he looked at it like this. He said, what if you took a beam of light and you shone it at something? You took a flashlight and you shone it at a wall, shined it at a wall. All right. What would it look like? Or you shined it at a distant planet, for example. What would it look like if you traveled alongside that beam of light at the same velocity? So in other words, you were traveling at the speed of light as well. Well, according to classical physics, that beam of light would appear to be at rest to you. All right. Now, imagine this. If you're driving up the Northway at 60 miles an hour, and the guy in the car next to you is driving at 60 miles an hour, well, then relative to each other, you're not in motion. You're moving at 0 miles an hour relative to each other. Okay. Now, if he's moving at 65 and you're moving at 60, then he's moving at 5 miles an hour relative to you. He's moving at 65 relative to the road, but he's only moving at 5 relative to you. And so that would be the classical interpretation. But Einstein concluded that if an observer could travel at the speed of light, he would still measure the speed of light as 3.0 times 10 to the 8th meters per second, which is the constant speed of light that you find on the front page of your reference tables. All right. And so this leads to all sorts of interesting questions that are derived from this theory of special relativity. Okay, so next thing, let's look at this in terms of one example with 3 different parts. All right, consider a spaceship moving away from a space station at half the speed of light. That's with this c divided by 2. All right, so half the speed of light, and the station emits a flash of light, just a quick burst of light. Now, if the 2 objects were not in motion relative to one another, then the spaceship, let's start with the observer. The observer on the station is going to observe the beam of light or the flash of light moving away from him at the speed of light, at c. Okay? That makes perfect sense if you think about it, right? You're standing on a space station, you flash a light, and the beam travels away from you at the speed of light. Easy peasy, right? Now, what if we get into the next scenario, though? What about the astronaut on the spaceship, right? According to Einstein's second postulate of special relativity, the observer on the spaceship also observes that light moving at c, the speed of light, 3.0 times 10 to the 8th meters per second. All right. Now, this can be a very tough concept to wrap your head around. All right. But it really has to do with the idea of what we call space-time. Now, and it's true regardless of the speed or the direction that the spaceship is moving. Now, what do I mean by space-time? Well, Einstein thought that uh, distance and time were actually part of the same continuum. If you're standing perfectly still, you are only moving through time. If you start walking, then you're moving through both space and time. If you are moving or walking, let's say, at the speed of light, then you are only walking through time. Uh, yeah, I'm sorry, only through distance. All right. The time is going to stand still because you're moving at the same speed that the light is moving. All right. And that's essentially what the space time continuum is all about. You can either move through distance, or you can move through distance and time, or you can move through time. All right. If you're sitting still, you're just moving through time. If you're walking, you're moving through space and time. And if you're moving at the speed of light, then you're only moving through space. Now, this brings up a wild theoretical experiment, um, which is referred to as time dilation. Consider a big clock in the middle of a village park, all right? And this clock reads that it's 12 noon, all right? If an alien on a distant planet aims a telescope at Earth and he sees that clock reading 12 p.m., it's going to be actually much later on Earth. All right. In other words, the time will have passed, but because it took 5 light years for the beam of light to reach the Earth. I'm sorry, to reach the alien's planet. It'll it'll read 12 o'clock, but it'll be really 5 years later on Earth. So look at it. In order to understand this, think about it this way. If you stand perfectly still, you're going to see the clock move into the future at a rate of 60 seconds per minute, right? That's how fast the hands on a clock actually turn, all right? But if you move away from the clock at the speed of light, you're actually moving parallel to that beam of light that says the clock is at 12 o'clock. And so the clock will always read 12 o'clock. Time will literally stand still. So if you have the ability to move at c, time will stand still. At that point, you're only moving through space, not through time. All right, and that's the concept of time dilation. If you move away at a speed that's less than the speed of light, you will see the clock advance, but because you're covering both distance and time, it's going to move in slow motion. All right, and so literally, time will slow down for the astronaut on a spaceship traveling at a speed close to, but not quite, the speed of light. And so the clock will advance, but it will do so in slow motion. All right, and this is the idea of time dilation. Now, we're going to get into this in a little bit more detail in the next couple of slides, but I wanted to give you that illustration, right? If you stand still, time goes on at 60 seconds a minute. If you're moving at the speed of light, the clock will never move. You're only moving through distance. But if you move at a speed less than c, the clock will advance, but it will advance in slow motion. Okay. So what else do we have about this time dilation idea? Well, let's say that this is a spaceship, all right, and it's moving through space at a very rapid rate, close to the speed of light, all right? And inside this spaceship, we've got a device called a light clock, all right? And the light clock is this thing right here, all right? And the white arrows represent a beam of light bouncing up and down and up and down, all right? The light clock itself is simply an empty tube with a perfect mirror at both ends. And so the light beam will bounce back and forth infinitely. It'll just keep moving back and forth and back and forth and back and forth. Now, to an observer on the spaceship, he is in an inertial reference frame. Even though the spaceship is moving at a gazillion miles an hour, he is not moving relative to the spaceship. And so the light clock will continue to send that beam of light bouncing back and forth. If the clock is stationary relative to the observer, which it would be in this case, it simply bounces up and down and back and forth. All right. And so time for the relatively stationary observer is going to continue on as normal. All right. Makes sense, right? You're in the spaceship, you got a clock on a wall, the clock's just moving, and you don't see any difference than you would see in any other scenario. Now, to an observer on the ground, this becomes very different, because now when the beam of light is flashed from the bottom panel here to the time it reaches the top panel, the spaceship has moved a distance which I'm going to refer to as L. And the distance that, crying out loud, the distance that the light has moved is this distance, which I'm going to call D. But the actual distance that the light has traveled is this, which I'm going to call S. So, excuse me. And so now we come into a scenario where we actually have a right triangle. If you look carefully, right, there's a right angle right here. Okay, so if the clock is stationary, the time is moving back and forth at a regular rate. But if the clock is in motion, all right, in a fast moving spaceship, an observer on the ground will see the light moving at a diagonal. Okay? Now, this brings us into the idea of time dilation. Because the speed of light is constant in space, it's going to take longer to reach the next mirror. All right, it's going to take a longer period of time to travel this distance S than it would be to travel this distance. And so we've got a difference in the amount of time. Now, let's have a look at this in a slightly different method. Let's look at it mathematically. Same picture now, all right? So the distance between this point and this point, I'm going to call L. This is the distance that the spaceship has traveled. I'm going to call this distance D, which is the distance that the light bounces back and forth between the two mirrors. But this distance here, I'm going to call S, all right? Now, couple of things. First, back in the old days, we said that V equals distance over time. Okay. Now, in this case, I'm going to say that the time is going to equal the distance over the velocity. Now, the distance that it's going to travel is, the light is going to travel, is 2 times the distance D. And the velocity is going to be C. All right. And so the original time that it takes, and we're talking really about the relatively stationary observer, is going to be 2 times the distance divided by this concept C. Now, if you look at the right triangle that we've drawn here, all right, we also have the idea that 2 times the length of the astronaut or that the spaceship has traveled is going to equal V times delta T, right? This is the overall distance, right? We're starting here. We're going all the way to here. That's 2 times the distance L. That's going to equal the velocity times the time, meaning that L is going to equal v delta t over 2. So the distance we travel is 1/2 v times t, or v times t over 2. Now, with a very quick derivation, the distance that we actually travel using Pythagoras' theorem, is going to be equal to this. 2 times the distance s is going to equal 2 times the square root of the d squared plus L squared. All right. Now, this started out as s squared equals d squared plus L squared. I took the square root of both sides and then multiplied it by 2. Now, and we know that the L is equal to v delta t over 2. So I'm going to rewrite this this formula as the speed of light times t. This is equal to 2s, equals 2 times the square root of d squared plus, now, L is equal to v delta t over 2. And so I'm going to replace L with that term in here. Now, if I square both sides and solve for t, and in the interest of time, I'm going to just give you the formula here. If I do this, what I'm going to end up with is delta t is going to equal 2 times d over c times 1 over the square root of 1 minus v squared over c squared. Now, since the original time is equal to 2d over c, this equals then delta t 0, the original time for the stationary observer, divided by the square root of 1 minus v squared over c squared. All right, and so that's going to equal, this is the formula that is going to be important here. Now, the derivation is not so important. I just wanted to show you where it comes from, and so that you can kind of have an understanding of what we're talking about here. Now, delta t is the time that passes for the stationary observer. Delta t 0. Delta t here is the time that passes for the observer on Earth. This is a 1, not an L. And v is the speed that the spaceship is traveling, and c is the speed of light in a vacuum. Okay? So how would we use this in an example problem? All right, so example number 1 in this case. So the example says a spacecraft is moving at 0.92 c. In other words, 92% of the speed of light. So whatever 92% of 3.0 times 10 to the 8th meters per second is. The astronaut, so in the stationary observer inside the spaceship, measures the time interval between successive ticks of the spacecraft clock to be exactly 1 second. Okay? We want to know, what is the time interval that an Earth observer measures between successive ticks? All right. So in this case, I'm going to, oh, come on now. I'm going to use the formula delta t equals delta t 0 all over the square root of 1 minus. Now, I'm going to cheat a little bit with the squaring. 0.92 c over c, that's the v and the c, and I'm going to square them both. Notice when I do this, the c's will cancel out, and so it's just going to be 1 minus whatever 0.92 squared is. Take the square root. So this becomes the original time of that the stationary observer sees is 1.0 seconds over the square root of 1 minus 0.92 squared. And if you do the arithmetic here, you find out that even though 1 second has passed for the astronaut in the spacecraft, 2.6 seconds have passed for the observer on Earth. All right. And so the person on Earth is aging at a rate that is about 2.5 times the rate that the astronaut is aging at. All right. That's a funky thing to think about a little bit. All right. So please think about it a little bit. All right. If 1 second passes on the spacecraft, then 2.6 seconds passes in or for the observer on Earth. Okay, meaning that if the astronaut was traveling at that speed for a year, he would age a year, but the people on Earth would age 2.5 years, 2.6 years. That's a pretty weird thing to think about. Okay, so in terms of this idea of time dilation, all right, what can we do with this? All right, well, in reality, on Earth here, because we do consider the Earth to be an inertial frame of reference, time dilation is not really appreciable. A jetliner traveling at 500 miles per hour would only lose 1 second every 100,000 years. All right, so just think about that. All right, in order to travel at 92% of the speed of light, I mean, that is an astronomical speed, really, really fast. And so, for our lives on Earth, this is not going to affect your day-to-day life. All right, if your buddy sits on a couch and you run out to Stewart's to get a candy bar and come back, and you're in motion the whole time, you're going to age a little less than he did, but not a significant amount. So, in order to get an accurate measurement, you've got to be in the same inertial reference frame as the clock. All right. So if the clock's in the spaceship, you have to be in the spaceship. If the clock's on Earth, then you have to be on Earth. All right. So that's how you do. That's what you would have to do in order to get this to work. So again, this is all very theoretical, because moving at the speed of light would be an exceptionally difficult thing to do for a variety of reasons. And actually, that's where the E equals mc squared equation comes in. The amount of energy that it would take to move a spaceship at the speed of light would be more energy than the sun produces in a year. All right, so it's beyond our wildest dreams at this point. But it's a nice theoretical exercise. Okay, so let's look at example number 2. Okay, in this case, we're going to start with another spaceship. So the star Alpha Centauri is 4.3 light years away. Now, I do have to point out right away that a light year is actually a unit of distance. All right, it is not a unit of time. All right, a light year is how far a beam of light travels in a year. Okay, so light from Alpha Centauri, like if we looked up at the sky right now, tonight, for example, and saw Alpha Centauri blow up, in reality, that happened 4.3 years ago. Okay, so whatever we see happen on Alpha Centauri today actually happened 4.3 years ago. Now, if a rocket left the Earth at 0.95 C, how much will the passengers have aged by their own clock when they reach Alpha Centauri? So, again, we're going to use the equation delta t equals delta t 0 divided by the square root of 1 minus v squared over c squared. Okay. Now, I'm going to rearrange this algebraically to solve for delta t 0. And that's going to equal delta t times the square root of 1 minus v squared over c squared. Okay. And so in this case, it's the first thing we have to do is figure out how long it would take to get to Alpha Centauri. Oh, come on now. So using the formula, delta t is going to equal the distance divided by the velocity. In this case, the distance is going to be 4.3 light years. What is going on? Divided by 0.95, and that's going to be, or give me, a time of 4.5 years. All right. So traveling at 0.95, the 0.95 C, it would take 4.5 years in order to get to Alpha Centauri. Okay. Now, let's start plugging and chugging here. So here, I'm going to put the 4.5 years in terms of the delta t value. Multiply that by, excuse me, the value 1 minus, and again, I'm going to cheat here, and I'm going to say 0.95 C over C, and take the square root. The C's can't, or square it rather. The C's cancel out. 1 minus 0.95 squared, take the square root of that, and then multiply it by 4.5, and you get a value of 1.4 years. So even though 4.5 years have passed on the planet Earth, the astronauts will only have aged 1.4 years. All right, think about that. All right, the people on Earth will be 4.5 years older. The astronauts will only be 1.5 years older. All right, this is pretty weird stuff. All right, but this is the theory of relativity. Okay. Now, relativity also deals with changes in distances, right? Because remember, the light is bouncing up and down and that kind of thing. Its distance will change as well. And so we want to know, what distance does the rocket actually travel? In this case, the distance, which is the L value, remember from earlier, is velocity times the time. Okay, and so in this case, we're traveling at 0.95 or 95% of the speed of light, and the time is 1.4 years. And so the distance that the thing actually travels is going to be 1.3 light years. All right. So the rocket, even though Alpha Centauri is 4.3 light years from Earth, because the rocket is moving at 95% of the speed of light, it's only going to take 1.3 light years to get there. All right. This is, again, really stuff that you have to wrap your head around. You really have to think about it for a while. Okay. In any event, this allows us to derive a formula similar to the last one, in that L equals LO times the same ratio or square root of 1 minus the square root of v squared over c squared. All right. So the actual length LO times the journey length L is here. Now, the length contraction doesn't just play a role in the distance that the rocket travels. It actually plays a role in the size of the rocket itself. All right. So, for example, in this example, let's say that the astronaut before the spacecraft takes off gets out a meter stick and measures the spacecraft as 82 meters long. All right. Moving at 95% of the speed of light, how long is the spaceship according to an observer on Earth? Well, in I don't know why this is doing this. I hate my mouse. L equals L0 times the square root of 1 minus V squared over C squared. That's going to be 82 meters. That's going to be the length of the spaceship on Earth in stationary form, times the square root of 1 minus 0.95 C over C squared. All right. And if I do the arithmetic here, remember the C's cancel out. I square the 0.95, subtract it from 1, and take the square root of that term, multiply by the value 82, and it turns out that the spaceship itself is only now 26 meters long. Okay, the spacecraft started out as 82 meters long. In travel, it's only 26 meters long relative to an observer on Earth. All right. That, my friends, is the end of that. I hope that I haven't blown your minds too badly. We'll talk to you later.